Hello everybody, welcome to another MCAT ACE lecture, and in today's lecture we are going to be discussing the functional group alcohols. So this will fall into the realm of organic chemistry because a lot of what we're going to be looking at is the functionality of how alcohols interact with reactions, whether it be making alcohols or once we have an alcohol, the type of reaction that alcohol can undergo. Now, with alcohols being very similar in structure to water, they are very prevalent biochemistry molecules. So this is going to be a very important lesson in terms of a specific type of functional group that you will want to know and master when you get to the MCAT. So, if you take a look, it looks like the list is very brief here. However, I will note that the synthesis of alcohols and the reactions of alcohols will take up the bulk of the time. So this is going to be a normal-sized lecture on this functional group. And even though the list here looks small, there's going to be quite a bit of information that goes into those two parts. So the overview is we're going to briefly discuss the physical properties of alcohols, especially what that OH group provides in terms of the polarity and melting and boiling points, things like that. We will also take a look at what's known as amphoteric behavior. So amphoteric is a term that's used when a compound can be either an acid or a base. And that's going to depend on the medium or the other reagents that you put that reagent into. So if you put an alcohol in with a strong acid, it'll act like a base. If you put an alcohol in with a strong base, it will act as an acid. So water is another example of an amphoteric substance. It's going to depend on the solution that you put it in terms of its behavior. Then we will talk about the synthesis of alcohols. So what types of reactions can we use in order to create alcohols? We're going to see there's a couple of hydration techniques that we can use using double bonds and triple bonds. So that would be alkenes and alkynes. We'll then take a little bit more of a detailed look at a well-known reaction known as the Grignard reaction. And the Grignard reaction is a very common way to make tertiary alcohols if you're working with ketones. Then we will also take a look at one or two other reactions in terms of making alcohols. So reactions of alcohols will follow that, and when we're dealing with reactions of alcohols, we now have the OH functionality. What types of reactions can we undergo with that alcohol? Certainly the opposite of hydration, we can do a dehydration. You can use some alcohols to create alkyl halides, which would then be good leaving groups if you would like to substitute the group with some other type of nucleophile, because OH groups by themselves, hydroxyl groups, are not great leaving groups compared to halides. So we can turn them into good leaving groups. And there's a couple other reactions that we'll take a look at, especially oxidation. Now I will mention, if you want some more detailed look at some of these, like oxidation reduction, you can also check out the aldehydes and ketones lecture, because aldehydes and ketones are the oxidized versions or states of alcohols, and so are carboxylic acids. So we have lectures on carboxylic acids and carboxylic acid derivatives, and then we also have the aldehyde and ketone chapters. So you're going to be exposed to a lot of this information on multiple fronts. So go ahead and check out some of the other lectures if you want a more detailed look at some of the mechanisms or things like that that can potentially go into those. And then at the end you can see I have this subject of protection of alcohols. So it is possible for certain functional groups to protect them. Now what does it mean to protect a functional group? It means that you are going to take that functional group, you are going to manipulate it or add some other functional portionality to that group in order to protect it from an upcoming reaction that it would normally interfere with. And once that reaction is done, you can deprotect the alcohol and get it back. So it's basically a way of protecting your alcohol from a reaction that it would normally interfere with, or maybe you don't want the alcohol participating in that reaction. And so we'll talk about some examples of when to protect your alcohols, because you don't want to be protecting your alcohol for every single reaction you go through. There are certain conditions that are going to be problematic to alcohols, especially if you have a very strong basic condition. So things like Grignard reagents, Wittig reagents, those are going to be problematic. And then finally, at the end, as always, we will have our review. So I will offer up some questions for practice, and then we'll do a summary, especially because we've got a whole cluster of reactions we're going to be taking a look at here, and we want to summarize that. So let's get started by taking a look at the physical properties of alcohols. All right, so an alcohol is going to take the general form of R, where R is the rest of the organic molecule, and then OH. So it's the hydroxyl functionality that is going to give rise to alcohol behavior. All right. Now this is different, even though you can talk about if an alcohol is able to leave a hydroxide. Hydroxides are in solution by themselves, right? So this is a base, and in fact it's a pretty strong base, whereas this, the alcohol, is an amphoteric substance. So this could be an acid or it could be a base, depending on what you place it into solution with, which again, we'll take a look at that in a minute or two here. But one of the important things we want to discuss or talk about with alcohols is the fact that alcohols are considered, by and large, unless there's high levels of symmetry and you might have a diol or something, they're going to be polar compounds. And that is because if you're talking about an R group, meaning the rest of the molecule, that's usually a hydrocarbon-based situation. So you're going to have a carbon attached to an oxygen attached to a hydrogen. Now, oxygen is a very electronegative element, so we're going to see some setup or behavior like this, where the hydrogen, this is a very large partial positive. This partial positive is not going to be quite as strong as the hydrogens would be because carbon is more electronegative than hydrogen. It can pull back a little bit more on the oxygen as far as the shared electrons. But the oxygen here is king as far as electronegativity is concerned. And so there's going to be a lot of electron density and a dipole moment headed in the direction of the oxygen of any given alcohol. So we know that alcohols are going to be polar. So when we think about that, that can be important for solubility with like dissolves like. So if you came across a question that had several compounds and it said, you know, what solvent would be best to dissolve this compound, you could take a polar compound and know that an alcohol or some other highly polar solvent would be ideal for that with the like dissolves like rule. So alcohol is on the polar end of the solvent scale, whereas things that are just hydrocarbons like hexane or butane's a gas, but pentane, all that kind of stuff, those would be considered non-polar for the most part. So alcohols will be polar. And then the other thing that we want to consider with alcohols is that they do have the ability to hydrogen bond. And again, this is very similar to an example with water, but because we have the partial positive and the partial negative end here, if I have another alcohol in solution, right, so I'll draw it out this way in order to align this properly, this partial negative will have an intermolecular force interaction with the partial positive hydrogen from the other alcohol, and then we would have the partial positive, and that would align itself with the partial negative of the other alcohol. So these strong intermolecular forces, which is often abbreviated IMF, okay, are going to be responsible for the increase we see in boiling points and melting points for a lot of alcohols. So when you compare alcohols to things like ethers, so an ether is similar, it's an RO, but then there's another R group. We don't have that H that gives the real big separation in polarity and electronegativity. Ethers tend to have a very low boiling point. In fact, it's just barely above room temperature for some common ethers, like diethyl ether. And you have to be careful with flammability for both alcohols and ethers, but especially for ethers because they are so volatile with that low boiling point. They can go into a gaseous phase very easily. All right, so the intermolecular forces, this attraction between alcohol molecules, is going to lead to an increased boiling point. And a lot of alcohols are liquids when we're dealing with them, but not all of them. And it's also going to lead to increased melting points. So we will see a jump in those physical property values in relation to the fact that we have strong intermolecular forces occurring here. We have lots of hydrogen bonding that can go on with alcohols. So, because alcohols are so similar to water, you have to be concerned in certain situations where alcohols might be present in a reaction that needs to stay dry. Now, dry means in chemistry terms in the absence of water. So certain reactions, they may have a liquid like hexane, but if you say I'm going to keep the reaction dry, you're saying I'm going to keep the reaction free of moisture. And alcohols many times, not all the time, but many times, will be considered right alongside with water some sort of form of moisture. And that's because you have this removable proton, depending on the situation. If you've got a strong base or something that reacts with acidic protons, the pKa of an alcohol is usually, now this can obviously be affected by resonance and inductive effects and things like that, but is usually going to be somewhere around 16 to 18. Okay? So water is usually quoted at being around 15.7. So it's real close in a lot of aspects to water as far as most of its properties are concerned. All right, now one of the things we wanted to talk about was the relation to acid-base chemistry. So I'm going to clear this, and we're going to take a look at two different cases here. So in the first case, we're going to take an alcohol. So again, we'll give an actual alcohol here. So let's do methanol. So in this case, we're going to have methanol, and I am going to show the proton separated from the oxygen here by a bond because we're going to talk about the reaction it goes through. Plus, let's take a look at a strong base. Now, when I say strong, hydroxide, because we just mentioned that that is strong, is not strong enough to effectively deprotonate alcohols. You need to get a little bit stronger. So some examples of stronger bases are hydrides, so hydrogens that have a lone pair associated with them. So this is spelled hydride. It's a hydrogen with a negative charge. We normally think of hydrogens as H+, or just protons. Okay, and another would be if you have some sort of an ionic amide. So if I have an NH2, think about NH3, that would be the neutral ammonia version. But if I had minus NH2, okay, these types of, they're called amide bases, are going to be very strong. So a lot of times they're paired with a salt, like sodium amide or sodium hydride. And when you work with these, you have to be very careful because these can get so reactive that they can interact with the moisture in air. So a lot of times sodium hydride and sodium amides, they are going to be stored in oil in order to prevent them from going bad or combusting in the presence of moisture. So let's use an example here. If I expose the methanol to a hydride, okay, and again, this would probably be sodium hydride or something like that, what is going to happen in a case like this? Well, this is most definitely a strong base from a pKa standpoint. So in that case, I expect that the alcohol will act as an acid because of the current conditions that I find it in. So if I were to look at how this is going to work, I would have the hydride coming in to remove the acidic proton, and these electrons would go over to the oxygen. That would be the mechanistic way of showing this acid-base reaction. So what are we going to expect once we finish this? Well, I now have CH3O-, and this is the new base, right? So this would be the conjugate base, and that comes from the acid. Because remember that when you do acid-base reactions, you're going to have conjugates here. So this methoxide is going to now be the current base that's in solution. And we would also form technically a conjugate acid of hydrogen gas. And this is going to be the conjugate to the hydride that was over there. Now, when we take a look at this reaction, many students will ask, well, isn't this reversible? Can it go back the other way? And the answer is no, that's not the case here, because methanol has a pKa of about 16, whereas hydrogen gas has a pKa of about 35, approximately, depending on what table you're referencing. All right. Now, the rule for acid-base reactions is that the lower acidity is going to predominate. So that means the higher pKa, because it's an inverse logarithmic scale, this is the weaker acid. Now think about what it means to be an acid. In the case of methanol, methanol is trying to send an H plus this way. And in the case of H2O, in the case of H2 gas, you're trying to send a hydrogen plus that way. All right. So if this is a pKa of 16, and this is a pKa of 35, right? The pKa of 16 is a much more effective acid. It's going to generate and send H plus over in this direction almost exclusively. You're not going to get much return in the other direction, all right? And this tends to happen if you have very strong acids or strong bases. You don't get that type of equilibrium dynamic. It is completely shifted to one side because of the pKa values. So note that if you jump in pKa, so let's say we go from 16 to 17, because it's a logarithmic scale, the pKa of 16 is 10 times more acidic than a pKa of 17. So in other words, if I had one acid on one side that had a pKa of 16 and on the other side the conjugate acid had a pKa of 17, the one that has a pKa of 16 is sending over 10 protons for every 1 proton that the other pKa of 17 can send back in the other direction. So you can see this is going to escalate quickly, because if I have a situation where it's a pKa of 16 to 18, we're now talking about the pKa of 16 being 100 times more acidic, right? And all I have to do is keep jumping. So to 19 would be 1,000 times. If I did it by a jump of 6, that's 1,000,000 times. By a jump of 9, that's 1,000,000,000 times. And then I can go to 1,000,000,000,000 with 12. So it continues to climb up and up and up when you're looking at that. So if you look at a pKa of 35, you're talking about methanol, in this case, being trillions upon trillions of times more acidic than the H2 gas. And that's important to understand when you're working with acid-base chemistry. All right, now, if we continue this and we take a look, I can also take methanol, same exact compound as before, right? And now I can place it in the presence of a strong acid. So let's say that I use HBr, for instance. So hydrobromic acid, again, you could use nitric or H2SO4, things like that. What am I going to expect in a case like this? Well, now HBr is most definitely an acid. And so if I'm going to place the methanol into this type of environment, the methanol is now going to behave as a base, not an acid, because there's already a much stronger acid that's present here when we're getting ready to look at this. So the behavior that I would expect is now, if methanol is going to act as a base, it's the oxygen with the electron density that will have the ability to come grab this acidic hydrogen. So if you look, it's the reverse of what we had up here, right? Here we had the base reaching out to the methanol to take that hydrogen. Now we have the methanol reaching out to the acid in order to take the hydrogen. And then the bromine would go ahead and leave. It's a very good leaving group. It will dissociate readily and take the excess electrons to become Br minus. So in a case like this, I would then expect the result to be that I have methanol, and it's going to be in a protonated form because it picked up an additional hydrogen. So one of its lone pairs was basically sent out and put on loan to this hydrogen. And this is now going to be the conjugate, and this would be acid in this case, because if it was acting as a base, I now expect it to be a conjugate acid. So then we would need the Br over here, and the Br would be the conjugate base. And that's going to be the result of the acid that we would have over here. So we would expect that an acid will give a conjugate base. Now, you should also keep in mind, this is just a general chemistry rule, the stronger an acid is, the weaker its conjugate base is going to be. And so if we take a look, HBr is a strong acid, so we're going to expect that that Br minus is going to be a very weak base. And on the opposite effect, the methanol is a fairly weak base if it's amphoteric. We wouldn't classify it as strong. So this protonated methanol is going to be a relatively strong acid in comparison. All right, so that takes care of the general acid-base reactivity. You can see that alcohol could behave as an acid or a base depending on the situation it is put in. So the next thing I'm going to do is I'm going to bring up some material to look at how we can create alcohols, the actual synthesis of alcohols. Alright, so I cleared the board and I have brought up a list of the various ways that we can now create or synthesize alcohols. So if you come up and you take a look at the list, we've discussed physical properties of alcohols, the amphoteric behavior with acid-base. Now we're going to take a look at the synthesis of alcohols, so how we can actually create them. Now, the first set, and I would say the first three of these 5 options, is going to involve double bonds, so alkenes. And when you get ready to work with them, you can use several methods in order to hydrate an alkene and give the resulting compound. Now, you can also create diols, meaning double alcohols, with some other reagents, but these are the 3 main methods that you utilize here. So, an alkene, we're just going to keep the example simple, is a double bond like this. In the case of acid-catalyzed hydration, the reagents are probably the simplest to look at. All right, now this does set up an equilibrium because you can have dehydration in a case like this. But what you would need is you would need some source of acid. A lot of times it's H2SO4, but you'll see different acids that can be used. And then you will also have some sort of an aqueous medium with that acid because you're going to hydrate. You'll need a source of water. So when you complete this, you will get what's known as a Markovnikov addition of an alcohol. Now, Markovnikov means that you will add the alcohol to the more substituted position of the two. So if you look, this is a primary position, this is a secondary position. So when you do this, the way that the mechanism would actually work is you're going to take the alkene, you would protonate it using this hydrogen here, and so that's going to leave you with an intermediate that would have a positive carbocation in the secondary position. And that's why it's Markovnikov, because the carbocation needs to land on that more substituted position. It is stabler for multiple reasons. You've got hyperconjugation, you've got some inductive effects that help out with that. The primary reason is hyperconjugation. That's why you want that positive charge in the most substituted area possible when it gets to looking at carbocations. So then at that point, the water would come in and attack that carbocation. You would regenerate, because notice it says catalyzed, which means we need to regenerate our catalyst when we're doing something catalyzed. So the water comes on, and then you need to remove a positive proton, an H+, from that water in order to get it to move over to an alcohol. Now, because we have a carbocation in this case, you can have potential rearrangement of the carbocation to, for instance, a tertiary position if there is one right next to the secondary position. So just keep that in mind. If you were to run through this reaction and the alkene was next to a more substituted possibility, you will end up with rearrangement that can happen in this reaction. Whereas the oxymercuration that we look at next will be a Markovnikov addition, but you do not have the possibility of rearrangement in that case. And that has to do, we're not going to look at all of it, but that has to do with the intermediates that are set up. You actually avoid carbocation formation in the oxymercuration demercuration. You only get some partial carbocation character there. So, oxymercuration demercuration. Again, we're dealing with alkenes. So I'm going to use the same example for the first 3 here. Now in this case, we end up with, first of all, some sort of a mercury reagent. That's where the mercuration term comes from. I have seen mercury sulfate, so HgSO4 is a common one that's used. In most undergraduate textbooks, at least that I've come across, a lot of times they will use the mercury acetate. So it's HgOAC, and then there's 2 of them. This is also combined with water because, again, you will need a source of water to hydrate. Now, the second step that's involved here uses NaBH4, which is a hydride reducing agent. So you have two steps. You've got the mercuration, the first step, that actually will use the mercury complex. It's going to form like a three-membered ring with the mercury complex, almost like an epoxide. You'll have the water that comes in and substitutes in the more substituted position, and then you eliminate the mercury complex and pick up an additional hydrogen in the second step when you use sodium borohydride. So the result is that you get, again, in the Markovnikov addition, an alcohol. Now this one, as I just mentioned, is not subject to rearrangement. So if we had a tertiary position directly next to the alkene, you cannot rearrange and put the alcohol in that tertiary position. So that's oxymercuration, demercuration. Now, this one's a little bit different. So when we take a look at hydroboration, hydroboration is still going to use an alkene, but when we use the alkene with hydroboration, we're going to actually get an anti-Markovnikov addition. So it's going to add the alcohol to the outer, less substituted area. And this also has to do with how the mechanism behaves and the first transition state. So we use a borohydride for hydroboration, BH3, or sometimes you might see it complexed as B2H6, which is just a doubling up of that reagent. But you have the borohydride, and then a lot of times you may see something like THF. That's a tetrahydrofuran. That's a solvent that you are using with the borohydride. And then in step 2, this is also a two-parter, you're going to need a source of peroxide, hydrogen peroxide usually being the most common, and then a base. So you'll usually use hydroxide in order to make this an alcohol functional group. So if you do that, what you'll end up with is the alcohol on this end right here. So your alcohol ends up on the less substituted position, the primary position, and this is the anti-Markovnikov. Okay. Now, when I say anti-Markovnikov, do not confuse that with anti-stereochemistry, meaning that you've added one group on the front face of the molecule and one on the back. In fact, this reaction has syn addition. So if you were starting to talk about stereochemistry, you would have added the OH to the front and the H to the front. So anti-Markovnikov talks about what's called regiochemistry, the region in which I am adding the alcohol. And then the syn and anti terminology refers to the stereochemical addition, and that is different than the regiochemical addition, which is, again, anti-Markovnikov here. So that is a list of examples where you can use hydration, in other words, adding water in some form, with alkenes. Now, one of the other major ways that alcohols are formed is through the process of reduction. Now, with reduction, we start to move away from alkenes, and we start taking a look at carbonyl compounds. So the carbonyl group is something that looks like this. It's a C double bond O. So you see this in many different functional groups, and you're going to see a lot of those appearing here. Ketones, aldehydes, esters, carboxylic acids, to name a few. You also would have amides, anhydrides, and other compounds like that. So with a reduction, the idea here is that you will take some sort of a carbonyl compound, and then you will bring this carbonyl down to an alcohol form once you are completed. Now, that alcohol could be primary, secondary, or tertiary, depending on what you're reducing with and the situation that you might have. Usually not tertiary. That's saved for Grignards. That's not usually accomplished through many reductions. But primary and secondary alcohols are very common to obtain when you do reduction. So I'm just going to sort of prelude these next two sections, which is reduction of carbonyls, and then we will talk about the Grignard reaction. If you want a more detailed look at all of this, check out, as I mentioned, the aldehyde and ketone lecture, and check out the carboxylic acid and derivatives lecture, because those lectures will talk about reduction and Grignard reactions in a bit more detail than we're going to get into right here. So when you have a ketone or an aldehyde, so let's just give ourselves a brief refresher as to what those look like. A ketone has R, C double bond O, R, and an aldehyde would be R, C double bond O, H. Those are two different types of carbonyls. Both of these carbonyls can be reduced using sodium borohydride, NaBH4, which we saw in one of the previous examples, and then it needs to be followed up with acidic conditions. Now these need to be kept separate from one another because reducing agents are going to generate hydrides, and a hydride, as we discussed at the beginning of this lecture, is an H-. It's a relatively strong base. So we would not want that to be in the presence of acid at the same time, so we keep that as a second step there. Now, what you will end up getting, if you do this, the hydride will attack a carbonyl and open that carbonyl up, and then when the carbonyl opens up and you get the CO-, you will then protonate that carbonyl with the H3O+. So, if you have a ketone and you subject the ketone to reduction with NaBH4, and I'm going to write reduction with a general R here, but we're talking about this reagent, you will end up with a secondary alcohol because it's R, you've added the H to that carbonyl, you've then protonated the alcohol portionality, and you end up with something like this. So you get a secondary alcohol. Now if I use an aldehyde and I reduce that, I'm going to end up with something different. So I reduce this, I'm going to have R, and then if you remember, there was not a second R to the right side of that aldehyde, it was an H. So this C, which has an H because of the aldehyde, would get a second H in the hydride substitution, right? So if the hydride was coming in here, and then it would have the OH here. So this would be a primary alcohol that we're working with. So ketones can be reduced into secondary alcohols, aldehydes can be reduced into primary alcohols. This is other ways that we can generate alcohols besides the hydration. Now, carboxylic acids and esters can also undergo this type of behavior, but when you do it with these, you're doing 2 times for your reduction. So you have to add a hydride, and then you're going to have to add a second hydride. And the way the mechanism works is that it kicks off either the OH group or the OR group, depending on whether you're working with an ester or a carboxylic acid. And you can take a look at that in the acid derivatives lecture that we have. Now, carboxylic acids and esters are going to need stronger reducing agents. The NaBH4 is not strong enough in order to reduce these down to their alcohol forms. So carboxylic acid is going to look like this. Okay, you can see very close similarities to the alcohol functionality. And then the ester, which would have a carbonyl, is going to be an OR group that we're looking at. Okay. So we would send the hydride in once, we would kick off these varying groups, and then the hydride, a second hydride addition would happen, and then you follow it up with H3O+. Now the stronger reagent that we require here is going to be lithium aluminum hydride. So that's often abbreviated as LAH, or sometimes you might see it as LiAlH4. That's lithium aluminum hydride. It will behave in the same manner, except more rapidly and more aggressively, as sodium borohydride will, by generating hydrides. You need to follow this up with H3O+, because you will still end up, after the hydride attack, having the opening of the carbonyl, and you'll need to protonate that. And both of these, when they are subjected to lithium aluminum hydride followed by acid, are going to give primary alcohols. So you'll get RCH2, OH, and this will be primary. The ester and the carboxylic acid both give primaries when they are reduced. Now, some students ask, can you use lithium aluminum hydride with ketones and aldehydes? And the answer is absolutely. The more aggressive reagent will work on the weaker reductions. There's no problem doing that. But you will run into issues doing the reverse. The sodium borohydride cannot be brought down to the carboxylic acids and esters because the kinetics of the reaction are painfully slow to non-existent, and you're not going to get a whole lot of reduction going on. You want to bump it up to lithium aluminum hydride in that case. So that's an important differentiation that you have there. Now, from a practical standpoint, sodium borohydride is much more stable and it's much safer to work with than lithium aluminum hydride. So in most teaching labs, in most experiences that you may have come across this reagent in your studies, you probably dealt with sodium borohydride. If you did, for instance, in an organic 2 class, a reduction of some sort in lab, you most likely use sodium borohydride or some other mild reagent, not the lithium aluminum hydride. So that covers reduction. Again, carbonyls are compounds that have this C double bond O. There are other carbonyls that can be reduced, but again, check out the lectures that I told you to look at and you'll see some more examples there of things like acid chlorides and anhydrides. They can all be reduced as well using the lithium aluminum hydride. So we now arrive at the Grignard reaction, which is one of the most prevalent reactions that students see throughout organic chemistry 2 when they're working with it. The Grignard reaction is a nucleophilic reaction. It also uses carbonyls, and it is very, very strong as far as its nucleophilic behavior. So a Grignard reagent is going to be an R group, a magnesium, which is kind of interesting because this is known as an organometallic. We don't come across many metals in organic chemistry. So you have an R group, a magnesium, and then you have a halide of some sort. A lot of times when I do my examples, I give bromide, but you could also have chlorine or iodide as additional halides in this type of situation. So what will happen is that this metal has a very strong partial positive association, and the alkyl portionality has a very partially negative association, to the point that many times you can almost think of this as R minus, okay, and Mg plus. It's so polarized that it's almost getting to the point where it's ionic. So that means that the R group is going to be the nucleophile in this case when we're getting ready to work with these reactions. So I can again do this with all the carbonyls that I have up here, with the exception of the carboxylic acid, because the acidic proton right here on a carboxylic acid will interfere and react with the R group, the R minus. So when you do this with, for instance, a ketone, so let's take a look with ketones. If I have R, C double bond O, R, and then I'm going to use, so we don't have too many R's confusing us, I'm going to use, let's say, CH3 MgBr. So that's my Grignard reagent. This also needs to be followed up with H3O+. Notice a lot of these steps require H3O+ at the end. That's because your carbonyl is going to go into some sort of an O- phase and you need to protonate it to get your alcohol. So in this case, the CH3 will act as a nucleophile. It'll come in towards the carbonyl, and this O will take on the formal charge. So when that happens, you're going to have O-. This O- will likely, in the meantime, before you get to your second step, couple with or complex with the magnesium, because you'd have Mg plus sitting here to help stabilize. All right, and then when you get ready to move to the second phase, and the CH3 has added here, you would then use the H3O+. So in that case, you've got H3O+. You would have the oxygen coming down to protonate. That would release water. And then what you end up with is R, C, R. We have a CH3 down here. And then you have an OH. So this is an example, because these R groups are carbon groups, of a tertiary alcohol. So we can now create tertiary alcohols using the method of Grignard reactions. All right, now not every carbonyl will give a tertiary alcohol. You have to take a look at what you're working with. So aldehydes, if you run an aldehyde through this same reaction, and I encourage you to pause the video, see if you can apply the mechanism and predict the outcome. So if I have an aldehyde with the same reagents, what do you think is going to happen? I'm going to run through it here, but pause and see if you could figure out what you would get. So CH3 MgBr and H3O+. So if you took the time to work through this, you should have found that you would end up with a secondary alcohol in this case. So we would have R, we would have CH, right? And then the CH would have the CH3 that adds, through nucleophilic addition when this comes in here, and then the O- would get protonated like this. So this is going to be a secondary alcohol if you run your aldehyde through. Now the ester, which is a little more difficult, and again, check out that lecture if you want to look at the exact mechanism. An ester is going to end up, just like a ketone, creating a tertiary alcohol when it works. Now the ester is interesting because when you have the Grignard reagent, you need to do it 2 times. So this is just like with the reduction, you need 2 equivalents of the Grignard reagent in order to do this. So one set will come in here, break open the oxygen, and then what's going to happen is this group will leave and the carbonyl will reform, and that intermediate form, if you had R, C, this reforms, you've now added a CH3. So this is a ketone because the OR left. A ketone, as we just saw, can undergo a Grignard reaction. So this ketone will undergo a second dose of Grignard, so you get another CH3 that's going to add here, and then at the end, just like a ketone would, you'll end up with a tertiary alcohol. So that is how Grignards can provide alcohols to add to our sort of toolbox as far as alcohol synthesis, and that really covers the bulk of the ways that you would have come across. So now that we are set with how to create alcohols, the next thing we're going to take a look at is the reactions of alcohol. So if we have an alcohol, what type of reactions can we undergo with? Certainly you're going to see some of the reverse reactions. So if we can hydrate to get an alcohol, we could also dehydrate in order to remove an alcohol and get an alkene back. We can also, for instance, reduction. If we can reduce something, we can also oxidize it and bring it back up. So we're going to see a lot of reverse reactions here in a minute. So let me clear the board. We'll take a look at the potential reactions alcohols can undergo, or at least the most prevalent ones, and then we will talk about protection before we head into our problem solving. So give me a second to clear the board, and then we'll take a look at that. Okay, so I cleared the screen here so that we can talk about the various reactions that alcohols can undergo. Now, the first one, without drawing out anything or getting into too much detail, is acid-base reaction. Now, keep in mind, if you wanted to look at this, we already discussed this at the beginning of this alcohol lecture series. We discussed the amphoteric nature of alcohols and then how they can behave as acids or as bases depending on the solution they're in. And we took a look at a reaction or two involving methanol. So just keep in mind, because we are talking about reactions of alcohols here, that alcohols can undergo acid-base reactions provided there's a strong enough acid or a strong enough base in solution. So one of the major ways that we created alcohols was hydration. So it would serve to reason that dehydration is the opposite process that can occur in order to remove alcohol functionalities. And we really, through the process of elimination, we really remove water when we're doing dehydration. And we really add water when we're doing hydration. We added a hydrogen, and then the OH group was also added in some form. So with acid catalyzed hydration, this is the reverse of the acid catalyzed, with acid catalyzed dehydration, this is the reverse of the acid catalyzed hydration. So when we work with something like this, typically this is with a tertiary alcohol. So you can get away with secondary alcohols, but usually tertiary alcohols are utilized here. So for instance, if I had a cyclic compound like this, and I had a methyl group here, and then I also had an alcohol on back. So there's a tertiary alcohol. So all that you really need in order to drive this process, which is in equilibrium with the hydration, is some source of acid, and then you want heat, because you are trying to add or well, you're trying to remove water, so you're going to try to add heat in order to drive that process forward through the equilibrium using Le Chatelier's principle. If one of the products is water, because you're dehydrating, it would serve to reason if we heat this reaction, it will increase the kinetics, but it will also drive the kinetics forward because we can remove water if we're heating it enough from the system, and Le Chatelier's principle would drive this forward then. So what happens here is that the alcohol is going to pick up the proton, the acidic proton here. We are going to get into a state where we have the H2O. So at that point, here's your methyl group that's still there. And then on the back, we would have, this is now water. So once this has become water, water is a very good leaving group in comparison to just a regular alcohol. So that will leave. Now, if you remember, I said that this is primarily used for tertiary alcohols. And the reason for that is that what is going to be left behind here is a carbocation. And tertiary carbocations are the most stable. That actually should not have stereochemistry since this is sp2 hybridized now. Okay, so that tertiary carbocation is a very stable intermediate in comparison to primary or secondary positions. So once you do this, you would then take an adjacent hydrogen. So for instance, we have two hydrogens down here, and you would remove one of them. Now water would do this because this is acid catalyzed. The water is going to grab one of these hydrogens, and then it would become H3O+, which is going to give you your H+ back in solution. So you'll get that H+ back because it's a catalyst. Now the electrons involved in that hydrogen bond are going to go into creating an alkene. So if you remember the hydration reactions, we worked with alkenes and we hydrated them in order to get alcohol. So now we're doing the opposite. We're taking an alcohol, dehydrating it, and we get an alkene as the product. Now, just as a side note here, we could have also pulled hydrogens off of this methyl group right here. So if that were to occur, you could also get a product that would look like this. Okay, so there's the double bond out there on the methyl group. Now this would be considered the minor product, and this would be considered the major product. And hopefully you remember, or you came across something that was referred to as Zaitsev's rule, or the more, basically what it states is the more substituted alkene is the predominating product, and that's due to stability. For the same reasons as hyperconjugation with carbocations, the p orbitals involved in the pi bonds are stabilized by hyperconjugation. And so the more substituted pattern you find around the alkenes, the more stable the alkenes would be. So this, when we talk about substitution, if you look, this alkene, let's switch colors here so that we can see exactly what I'm talking about. This double bond right here is going to have an R group here, an R group here, and an R group here. So this would be a hydrogen coming off of here. So we would call this tri-substituted. Okay? Now you can get up to tetra-substituted with highly substituted alkenes, and you could get technically as low as a mono-substituted alkene, depending on what you're looking at. So in this case, this would be a di-substituted alkene because we have an R group here, we have an R group here, but then there are only hydrogens coming off of there. All right? So just important to remember when you're working with dehydration that you need to keep in mind that Zaitsev's rule will apply to any potential products. So you will certainly get a mix of these products, but it will be the most highly substituted one that will be the predominant product when you're working with this. All right, now POCl3 it's an acid. It's a Lewis acid, so it's an electron acceptor. And when you use POCl3, it will do the same thing as the acid catalyzed. However, it does not create carbocation intermediates. And because of that, the POCl3 reagent is utilized for secondary, and sometimes you can get away with some primaries using POCl3. But secondary, and this would still work for tertiary. There's no reason that you can't use it for tertiary. But the acid catalyzed gets a little bit more limited when you start working with the secondary and below. So this is typically used more for secondary and primaries. And then you can acid catalyze if you'd like. Or if you're looking to avoid harsh acidic conditions, because you need a strong acid in order to do what we just showed in part A here, you can use POCl3 as something that's a little bit milder. So in order to do this, I'll show the same example. You will have an alcohol. This time we can just do a secondary alcohol because that's sort of what the context of this example is showing. And with this, you would use your POCl3 reagent. A lot of times this is included with pyridine. Pyridine being an aromatic base compound. And what you will end up with is your dehydrated alkene. So dehydrations will provide alkenes when you are working with any sort of alcohol to start with. Okay, so that is one reaction that alcohols can undergo. Now, one of the other things that we took a look at was reduction. Now, oxidation is the complement to reduction. And again, I will point you towards the aldehyde and ketone lecture and the carboxylic acid derivatives lecture if you want further detail related to some of this. But when we have reduction, we can use oxidation as basically the complementary reaction. And so this will take alcohols and bring them back up into carbonyl compounds. So there are weak and there are strong oxidations. A weak oxidation is going to utilize PCC. That's the most common reagent. Now, you may also come across something known as the Des-Martin reagent. That is also used for weak oxidation, but PCC is by and large the most common out of the bunch that you're going to find. So when you utilize weak oxidation, you're going to use most of the time a primary alcohol. Now, it's not that it can't work with secondary alcohols, it can, but there's no difference between using weak or strong oxidation with a secondary alcohol. So what will happen is you take your primary alcohol, let's use ethanol as an example, and when you have your primary alcohol, you use PCC. A lot of times you might see a solvent underneath here like methylene chloride, so that is CH2Cl2, or you might see some other like carbon tetrachloride or something like that. So what will occur is that the alcohol that was originally reduced in the previous section we were looking at will be oxidized back up into a carbonyl compound. Now this oxidation will occur on the carbon that is attached to the alcohol. So that CH2 there is going to become the C double bond O. So you have the CH3, and then the CH2 becomes a C double bond O. Now here's the technique. When you use PCC, it will only make an aldehyde. If you use one of the strong oxidizing agents on a primary alcohol, it's going to create a carboxylic acid. So if you think about a carboxylic acid would have an oxygen in between this carbon-hydrogen bond there. So that's a further level of oxidation that's occurring at the site of that carbon. So because that's a more intense oxidation, that is reserved for the strong oxidizing agents. Now, speaking of strong oxidation, there's many different strong oxidizing agents that you can utilize. I put the two most common reagents here that you would have probably come across in an undergraduate organic chemistry course, and that is potassium permanganate, KMNO4, and the CrO3. Now again, you may have come across something like Na2Cr2O7, like some sort of a chromate compound or chromic acid. Now, when you are working with these, they will be in acidic conditions. So you're going to see H3O plus with these most of the time. Because the strong oxidizing agents are in an acidic aqueous medium, it's not like we saw with the Grignard reaction or the reductions where you need to put 1 and then 2. This would occur in the same step. And these reagents, the KMNO4 or the CrO3, would be in an acidic medium. They don't have to be separated from it. So when you would work with this, if you were to do the primary alcohol, again we'll use ethanol as an example, as we just said a minute ago, doing the strong oxidation is going to provide a carboxylic acid. So we'll use KMNO4 with H3O plus here, and when you oxidize ethanol using that, you would end up with acetic acid. Now, if you use a secondary alcohol, you're going to end up with a ketone. So let's say that I have an alcohol that looks like this. If I use an oxidizing agent here, a strong one, I am going to oxidize this into acetone. I'm going to get the corresponding ketone. Now remember, as I said a minute ago, you can use the PCC, you can use the weaker oxidation method on a secondary and you will still get a ketone. It doesn't matter. Because when you have this secondary position, you don't have the ability to create further oxidized species such as a carboxylic acid. So no matter what reagent you choose, if you have a secondary alcohol, you are going to get a ketone when you oxidize it. Now tertiary alcohols will not oxidize, and that is because there are no hydrogens on the carbons, like this hydrogen right here, that involve the alcohol. So if you notice, every carbon involved in the alcohol bond in these examples had hydrogens available for removal, right? So in a reduction, we add hydrogens with the hydride reagent. So it would make sense in oxidation, we're going to have to remove those hydrogens to increase the number of potential carbon-oxygen bonds. So if you have a tertiary alcohol, let's say something like T-butanol, right? If I have something like this, the carbon that is directly attached to the alcohol does not have any removable, what we would call alpha hydrogens. This carbon right here has a complete lack of hydrogens. And because of that, we cannot oxidize this species. And if we attempted to, even if somehow you could create a double bond, the problem at that point is that you would then have a carbon with 5 bonds. And that goes into surpassing valence rules where you are not permitted to have more than 4 bonds in relation to a carbon atom. So that takes care of oxidation, which was the complement to reduction. Now, one of the last reactions we're going to go over here is halogenation. So if you remember at the beginning of this lecture session, I stated that alcohol, if it's not protonated into water, if it's just OH, is not a very good leaving group most of the time. There are rare occasions where it can be. So one of the things you might want to do is get rid of an alcohol, but let's say you want to bring in a group like an amine, an NH2 group. You cannot directly substitute and use an NH2 nucleophile to come in and kick off the OH. You would need a better leaving group that would create a weaker base when it leaves. So halogens are ideal candidates as leaving groups in those situations. So it's very useful to be able to take an alcohol and turn it into a halide. And that's exactly what we're going to look at here. Tertiary alcohols can be utilized with acid. Now the acid needs to be an acid chloride. So when we're talking about this, we're talking about HCl or HBr. You could also use HI. But we need one of those strong acids that are associated with the halide. And that's important because the halide is going to act as a nucleophile at the end of the reaction when we're working with it. So if I have a tertiary alcohol, let's draw an example here. So I've got a methyl group here, and I have an OH here. If I take a look at this tertiary alcohol, and I utilize HBr, the first thing that's going to happen is acid-base related. And you should know this based on the amphoteric discussion we had at the beginning of this lecture. The alcohol, in the presence of a strong acid, is going to behave as a base. So it's going to pick up this hydrogen, and the Br is going to leave into solution as a weak base with the electrons. This is going to lead to an intermediate where we have a protonated water. And we saw behavior like this in several other reactions including the dehydration. CH3, and instead of OH, we now have water. Water is a good leaving group because it's neutral when it goes into solution, unlike just an alcohol, which would be minus OH. That's a strong base that would be in solution. So this group will leave, and when it leaves, it will create a carbocation. Again, if you notice, tertiary alcohol is the suggestion for this reaction here. And tertiary is important because tertiary sites will offer up better carbocation stability. And that's been a going theme as we've looked through multiple reactions. So here's the carbocation. The water is left at this point. The bromine can now come in as an effective nucleophile to the carbocation site, and we will end up with our halide. Because this carbocation is trigonal planar and sp2 hybridized, when the bromine comes in, it could attack from either side. So I'm going to show one of the two products here, which will be the Br in the front, or coming out of the plane, and the methyl in the back. However, you could easily get the inverse of this. So it is possible, I'm going to put plus here, to get give me a second here. You can get the Br coming in through the back and the CH3 up front here. Now, you need to realize that this doesn't always lead to a case where you might have enantiomers, because if this is a methyl group and this is a methyl group, this is a methyl group and this is a methyl group, it doesn't really matter as far as stereochemistry and do I have one that's R and one that's S, so on and so forth. So just keep in mind when you're working with this, I'm showing this here in case it ever did come up in a situation where you had 4 different groups. But you don't really need to worry about this as much unless you're getting into a case where you could potentially have enantiomers or diastereomers or some sort of stereochemical outcome or difference. But it's important to realize that when you're dealing with trigonal planar intermediates. So if we have secondary or primary, similar to the dehydration, if we're going to use a carbocation, we have to be aware or conscious of the fact that carbocations are mildly stable in secondary positions and not stable at all in primary positions. So we like alternative methods if possible when we start dealing with secondary and primary forms. In the case of turning these alcohols into halides, if you have a secondary or a primary alcohol, there are reagents that will behave more in an SN2 type manner, and that is PBr3 or SOCl2. So PBr3 will give you a bromine, respectively, and SOCl2 will give you a chlorine, respectively. So if I take a compound, and this time we will do a secondary alcohol, so we'll put the OH here, and then this is just a hydrogen instead of a methyl this round. You can use PBr3 or SOCl2. We'll go ahead and use PBr3. Again, you might see solvents like ether or pyridine or things like that that appear with these reagents. And once you run through this, you will end up with the Br. Now notice that I'm putting an inverted position here because this does occur through SN2 type mechanics, which is backside attack, and you've got the inversion of the stereochemistry. So that is possible, and again, if you use the SOCl2 down here instead of the PBr3, you would end up with a chloride instead of a bromide. So those are some options for turning alcohols into alkyl halides in case we wanted to create leaving groups and allow for other types of nucleophiles to come in and replace the position that the alcohol originally had on the functional chain. So that covers the main reactions that we would want to consider for alcohols. So what I will do now is I'm going to delete the board and we will take a look at protection of alcohols briefly. I don't want to get too far into this, but we'll take a look at that and then I'll bring up the review questions. So let me clear the board and then we'll take a look at protection of alcohols. Okay, so moving on to protection of alcohols. I'm going to talk about one or two notes that I have up here, and then I'm actually going to show the reaction involving a protection of an alcohol. So alcohols are protected from reactions that you would not want them interfering with. So sometimes alcohols will just sit on the compound, they may not react at all, but there may be other reactions where alcohols from a functionality standpoint would interfere with the reaction, and you're not looking to have that happen. So you will always deprotect the alcohol because you're looking to get it back at the end of the reaction or reactions, because there may be multiple reactions you're looking to protect the alcohol from, and then you want it back at the end. So the most common way to do this is creating an ether, because ethers are much less reactive than alcohols are from a functionality standpoint. Now, there are many different types of ways that you could protect alcohols, but we're not going to list all of them here. We're going to look at the most common one, which is the creation of a silyl ether. So silyl is referring to the group silicon, Si, which is very similar to carbon. If you look at a periodic table, it's right underneath it. So the behavior is similar. And the TMS functionality is trimethylsilyl. So it's going to involve 3 methyl groups, similar to what we saw in the T-butanol example, and those will be connected to the silicon. So this would be a trimethylsilyl group, and this would be what you attach to the other end of the alcohol. So you're looking at something like this when you're fully protected, whereas this oxygen was originally OH from an ROH group. So that's what your alcohol looks like when it's protected. The way that you do this is with trimethylsilyl chloride. So you'll take an alcohol, we're just going to use a generic example, ROH, and if you want to protect the alcohol from some sort of an upcoming reaction, what you would do is you would use TMSCl. So trimethylsilyl chloride is this whole structure right here, but instead of the OR group you have a chlorine. The alcohol is going to come in and replace the chlorine, nucleophilically speaking, and then you will have the protected alcohol as a silyl ether. That's the way that we do this. Now, because the alcohol is protonated here, when it comes in as a nucleophile, it's going to bring that protonation with it. You need to remove that, and typically you will have pyridine or some other type of base that's utilized along with the trimethylsilyl chloride to help accomplish that. So when you're done, you'll get RO and then TMS, where TMS represents the trimethylsilyl group. It's very easy to remove trimethylsilyl group. So when you're ready to deprotect, all you have to do is run this reaction through acid. So one of the things that tells you is that if you are trying to protect the alcohol from acidic conditions, you're not going to use a trimethylsilyl group, because trimethylsilyl will fall apart in acidic conditions. And most of the time when you're protecting alcohols, you protect them from bases more than you do from acids, as a general rule. So when we get ready to look at an actual example where this might be important, let's say that I've got a compound that looks like this. So I've got CH3, C double bond O, CH2, CH2, OH. And this compound, I would like to run a Grignard reaction. So I'm going to do methyl magnesium bromide as the first step, and then I would follow it up with acid. Now the problem with how I've currently written this is that CH3 is a very potent, the CH3 in the Grignard reagent is a very potent base and nucleophile. So the behavior that I'm looking for, if you follow the purple arrow, is for an attack at this carbonyl and for this to open up. But when I switch over to this red arrow, this is what's actually going to happen. The alcohol is acidic enough that the Grignard is going to grab and take that proton long before it behaves as a nucleophile. And that's going to screw up the reaction. So I'm going to have a competing side reaction with the alcohol that I'm not looking for. I want the Grignard to go in and attack the carbonyl, not attack the alcohol. So this would be a perfect case where I would say, instead of doing the Grignard first, step 1 is that I need to protect this with the TMSCl and the base. And once I've protected the alcohol, then the Grignard can become step 2. And then in step 3, not only will the H3O plus finish off the Grignard to give me the new alcohol, but if I have enough excess acid, I will also cleave the TMS back off and recover this alcohol in the 3rd step. So that's a practical example where I would need to use a protecting group in order to do this. Now, protecting groups can also come into the pharmaceutical and medical field when you start talking about drugs, because many drugs will have sensitive functionalities that could easily fall apart when they get into the acidic conditions of the stomach or the basic conditions of the gut or what have you. So when you get ready to look at certain drug designs, sometimes if there's an important part to the drug that's going to be affected by acidic conditions, let's say, many times pharmaceuticals will turn around and they will latch on a protecting group so that when they go and give the drug and it passes through those conditions, that part of the functional group will be cleaved to the protecting group, or it will protect it and get cleaved later in the body in order to deliver the drug without it breaking down. So this is applicable outside of just the organic lab, where you could start applying it to pharmaceuticals and the medical industry. And obviously, those are important connections to make when you're dealing with MCAT-related material. So that covers protections of alcohols. We're now going to put up the questions, the review questions, and then we'll obviously do our summary at the end. So let me clear the board off. I will bring up the review questions for alcohols, and we will go ahead and take a look at those together. Okay, everyone, so I have brought up the questions related to alcohols, and we're going to take a look at them briefly. And as usual in most of these lessons, you are encouraged to pause the video and attempt to work through each of these yourself to the best of your ability. And then when you feel you need a walkthrough or you've answered all the questions and you think you're ready, you can go ahead and unpause and we will walk through these questions together. So let's take a look at them. Number 1, which of the following would not be a method for creating a secondary alcohol? You've got a couple of options there. You've got some wording, so because it's words and not structures or reagents, you're going to need to know what those functional groups and reagents would potentially be. Number 2, which reagent set would complete the transformation shown here? So we've got an alkene, and it's going over to an alcohol. So this is a type of reaction that we've discussed during the creating alcohols portion of this lecture. And you've got several different sets to work with there. You want to pick the best set of reagents that would provide you with the product you see over on the right. Number 3, in the reaction shown here, the alcohol would most likely, and there's several options. So take a look at that alcohol. You've got sodium amide and acetone, and you need to decide how the alcohol is going to behave in the situation that's set up. So those options are the possibilities. And then number 4, which of the following would be the major product of the given dehydration? So we're going to do an acid-catalyzed dehydration. You have a tertiary alcohol in this case, and you could have one of several products. So this is really a major versus minor type of question when we're looking at the products based on Zaitsev's rule. So taking a look at these, here are the 4 options. You would need to pick out and hopefully be able to justify to yourself which one would be the major product and why, and we'll take a look at that. So as usual, I'm going to scroll through these one more time. You can pause to take notes or write things down. These are the 4 questions that you are looking to address, and then when you unpause the video, we will go through them together. Okay, so go ahead and pause the video, and then I will see everybody for the walkthrough when you're done. All right, so hopefully everybody had a chance to work on these problems. We're now going to walk through each of them and explain the answers that would be best in each case. So number 1, which of the following would not be a method for creating a secondary alcohol? Well, let's take a look at these methods and consider whether we could get a secondary alcohol based on what they are asking or providing. So A, hydration of alkenes. So if I were to create an alkene, and you might have to do several different examples if you couldn't get the first one to work, but as soon as you could get one to work that's plausible, you could move on. So if I have an alkene here, could I hydrate it so that I end up with an alcohol in that secondary position? Well, the answer for this would be yes. There's plenty of options. I could do an acid catalyzed, I could do an oxymercuration. Those would both give hydration sites here for the secondary position. So that is an acceptable choice. Now, B, reduction of ketones. So if I have a ketone, which is R, C double bond O, R, and I reduce it using any type of reducing agent that would provide hydrides, it might be NaBH4 or it might be lithium aluminum hydride, I will end up with RCH with the OH here and then another R. Well, that's a secondary alcohol, so this would also meet the test for creating secondary alcohols. C, a Grignard with aldehydes. So if I were to take an aldehyde, which looks like this, and subject it to a Grignard, the Grignard being, again, the common one we've used has been methyl magnesium bromide, right? That's step one. Step two would be the acid. If I were to do that, the CH3 is going to come into this position here, and then that O involved in the carbonyl becomes the hydroxyl. So if I look at this, I've got R, and then I'm going to have CH, I'm going to have the CH3 that attaches to that CH from the Grignard, and then I would have OH. This is also a secondary alcohol. So by default, the last one must be the answer as far as a method that is not acceptable for creating a secondary alcohol. And if we take a look at that reduction of aldehydes, if I were to take an aldehyde and reduce it, it would turn into a primary alcohol. So R, C double bond O, H. If I reduce this by providing H minus, similar to the example B with the ketones, that H would come in here to create a CH2 at that site, and then I would follow it up with H3O plus, and that would turn the O minus into an alcohol. So I've got R, CH2, OH. This is a primary alcohol. And so D would provide a primary alcohol. It would not be acceptable for creating secondary alcohols. Hopefully everybody was able to arrive at that answer. Number 2, which reagent set would complete the transformation shown here? So let's do a little process of elimination, because that's always useful if you are against the clock while you're working on the MCAT exam, and you can easily get rid of some of these types of problems in a standardized testing situation. So let's take a look at what I'm doing here. I've got an alkene, and I am taking that alkene over to an alcohol. That must be some form of a hydration reaction. So do I have hydration reactions here? Is A a hydration reaction? Yes. Borohydration, or hydroboration, is going to be one of the hydration reactions. So that one we can keep for right now. What about B? A Grignard reaction. That is not a hydration. Even though we will create an alcohol, the Grignard reaction is a nucleophilic addition, and it adds to carbonyls. We don't usually see it adding to alkenes. So this is going to be out for right now. C, that one is considered to be a hydration reaction. This is acidic hydration, acidic catalyzed hydration, so that's open. And then D, PCC in methylene chloride, that is an oxidation, not a hydration. So that would take an alcohol to an aldehyde or ketone. So oxidation and Grignard are out. That leaves A and C. We're down to a 50-50 now. So what we would do at this point is say, of these two hydrations, what would I expect? So if I were to look at the acid catalyzed, which is the H plus H2O, that's C, okay, then what I would expect is the Markovnikov addition of the alcohol. So the alcohol would add to the more substituted position, meaning I should find the alcohol where the methyl group is, because that's a tertiary position in comparison to a secondary position. So that would not work, and through that process of elimination we're left with A. Now, does A make sense? Yes, the hydroboration reagent, when you take a look at it, is going to add anti-Markovnikov. It should add the alcohol to this position here, the secondary position. And that's exactly what we see here. And notice that the hydrogen that was also added, because H2O is what's added in total when we do a hydration, they were both added syn. So this has syn stereochemistry, and the regiochemistry is anti-Markovnikov. And so that works out perfectly as far as the product that we're seeing there. So A would be the best choice in this scenario. 3. In the reaction shown here, the alcohol would most likely do what? Well, let's take a look at what we would expect and see if one of the options would fit that. So, I have an alcohol. I don't have any other type of functionality present except the alcohol. It's just a regular alkane chain. I then have NaNH2, which would be sodium amide. And when I take a look at this, I could expect in acetone that the polar behavior of this compound would be in effect, so it would create a salt like this. Now, this right here would be labeled as a very strong base. And if you remember our amphoteric discussion, that was what we stated when we brought up sodium hydride and sodium amide. So what would we expect if an alcohol was in the presence of this very strong base? Well, if it's a strong base, the alcohol would most likely give its proton over to that strong base, making the alcohol behave as an acid. And because there's no other functional groups here, I wouldn't really expect the NH2 to interact with anything. There's no carbonyls, there's no alkyl halides or anything like that. So I'm pretty much pigeonholed into looking at an acid-base reaction in this case. So let's see if something fits that. A, I would expect the alcohol to act as an acid, donating its proton. That already sounds pretty good based on what we just said. So let's table that and just make sure none of the others sound like they would work, and then we'll move forward. B, the alcohol would act as a base, accepting a proton. Not with NH2 already being a strong base. If there was a strong acid, then the alcohol might act as a base, but that one's definitely out in this case. C, the alcohol will need to be protected in order to allow the amide, the NH2, to undergo an SN2 reaction. This is out because even though this could potentially be a nucleophile, where is it going to substitute in that nucleophilic addition? There are no alkyl halides. For instance, maybe if there was a chlorine here, we could consider a situation like that, or some other type of leaving group. This would probably still act very aggressively as a base rather than a nucleophile in a case like that, but because we don't even have any leaving groups, we don't need to consider it. So that is out. D, the alcohol would be oxidized to a carbonyl due to the nitrogen being electronegative. While that might sound tempting because nitrogen is electronegative, and we have talked about oxidation and oxygen being electronegative, this is out. And it should be out simply on the fact that if we're talking about oxidation, we already learned reagents. We would expect to see something like PCC or one of the chromium reagents or KMNO4. I don't see any of that here. I see NaNH2. And so A is most definitely the proper answer when we're looking at this. All right, 4. Which of the following would be the major product given the dehydration shown? So if you were to take a look at this, keep in mind that when this alcohol protonates and leaves, we're going to leave a carbocation right here on that top portion. My plus charge got a little screwed up there. There you go. That's where the carbocation is going to land. So if that's where the carbocation is, we can only take adjacent protons. So that means there is a proton back associated. It's implied, but there is a proton here. There are adjacent protons on this CH3 group, and there are adjacent protons on this carbon right here. There's 2 of them. It's getting a little crowded here, but there would be an H there, and there would also be an H here. Those are the options. So the ones that I select in red here are not going to be options. So these carbons do not have hydrogens that would be removable in the proximity to the carbocation. You need to be adjacent when you're doing this elimination. So those are out. So let's take a look at the potential options here. Would A be a plausible option? Yes, A would make sense. I'm going to switch colors here again to purple. Okay, so if we take a look at A would make sense because that's utilizing one of the protons that we have right here, right? I'd have to remove one of them. The alcohol was removed with the carbocation, and that provides that alkene right there. Now, if I take a look at this alkene, the key to this whole entire scenario is going to be which compound, if it's a legitimate one, has the highest level of substitution around the alkene, right? That's what we're looking for in terms of hyperconjugation and Zaitsev's product. So this is off to a pretty good start because if I take a look at this one, I've got one group right here, I've got a second group right here, I've got a third group right here, and then there would be an H coming off of here because I didn't need both of those H's. I only required one for the elimination. So if I am to consider this option, this would be a tri-substituted option, and it does look legitimate in terms of where I pulled the protons from. So that's in the running, and it's fairly high in its substitution pattern. So let's look at B. For B, if I wanted this would be a tetra-substituted, so that is even better than A. This would be our candidate in the running at that point, but it doesn't make sense. Can I do that? Well, there is a proton associated with this carbon right here. So this is a legitimate dehydration candidate, therefore a legitimate product, and this is now definitely the one that's in the running. We can eliminate A because B would be the major product at that point. C would be a minor product. Now, does it actually make sense? Well, that CH3 is now being turned into a CH2 because of the removal of one of the protons. So yes, that is an acceptable candidate. However, it's out of the running because this would only be di-substituted, right? We have two H's because this is CH2 coming off the other end. So that is out as a potential candidate. And if you take a look here, D is also out because D is placing the alkene in one of the areas that we said we would not have removable protons to work with, right? It's too far from the carbocation. So D is out automatically just because you couldn't even create this product, let alone have it as the major product. So that leaves B as the correct answer. That would be the Zaitsev product, the most stable and most likely the most highly formed product in this case. So that takes care of the review questions for the alcohol lecture series. What I'm going to do now is clear the questions and clear up the board. We're going to put a summary that I'll run through briefly, and then we will be all set with the alcohol chapter. So give me a second to clear the board here, and then we will go over the summary. Okay, everyone, so here's the summary for alcohols. And keep in mind that even though the original overview was relatively small in terms of what we listed, we said that this was going to be a pretty comprehensive or large amount of material that we were going to have to cover. So you'll expect to see that in the summary here. So the first thing we discussed was that the OH group for an alcohol provides strong intermolecular forces with hydrogen bonding. And that means that we would expect to see increased boiling points and melting points in comparison to other slightly more nonpolar compounds such as ethers. This also means that small-chained alcohols that don't have tons of hydrocarbon property to them are going to likely be soluble or miscible in other polar compounds like water. We know that alcohols are amphoteric, and this definition means that they can act as either an acid or a base depending on the medium that we put them in. So if we put them in with a strong acid, we'll expect to see them behave as a base, or if we put them in with a strong base, we'll expect to see them behaving as an acid. Now, there's multiple ways to synthesize alcohols and create them. So the first that we looked at was alkene hydration. And we had three various options when we were looking at that. The first one was an acid catalyzed hydration, which used primarily just an acid catalyst and water. When we used that, we saw Markovnikov addition with a carbocation intermediate. So this specific reaction was subject to potential rearrangement because of that carbocation. Now the oxymercuration provided a Markovnikov addition. However, there was no formal carbocation intermediate when we were looking at the reaction itself. The hydroboration, which was the third option, was an anti-Markovnikov addition. So that one allowed us a little bit of a different angle or approach to the hydration, where we could put the alcohol in the less substituted position when we used hydroboration. So all three of these have their purpose when we're looking at them in terms of what they can deliver. The second reaction that we looked at that could create alcohols was the reduction of carbonyls. And we used two different reagents. The first was sodium borohydride. That was utilized with ketones and aldehydes. And remember that ketones would reduce down to secondary alcohols, aldehydes would reduce down to primary alcohols using that method. If you need something stronger, you can use lithium aluminum hydride. Lithium aluminum hydride is primarily used on carboxylic acids and esters. Because of their higher oxidized state, they need a more powerful reducing agent. However, you could still use lithium aluminum hydride on ketones and aldehydes, and it would work perfectly well. The third reaction we went through was the Grignard reaction. We said that for aldehydes, you would get a nucleophilic addition, and you would end up with a secondary alcohol. For ketones and for esters, you end up with tertiary alcohols when you do the Grignard reagent. And also keep in mind that when you deal with esters, you have a double Grignard reaction. So the first equivalence of Grignard reagent will take the ester to a ketone. The second one will then, just as with a ketone, react with a ketone intermediate and take it down to the tertiary alcohol. So, in terms of the reactions of alcohols, once we finished how to actually create them, there were a few. We had dehydration. For tertiary alcohols, we found that we could use acid-catalyzed dehydration, usually something like H2SO4, and heat helped to drive that reversible process forward with the removal of water, since we are removing water as part of this reaction. When we took a look at secondary and below, you can use the POCl3, which is a Lewis acid. It's a bit milder, and you are able to get away without carbocation formation, whereas the tertiary does have carbocation formation if you're using the acid-catalyzed process. You need to keep in mind that you have to follow the substitution rules for alkene products. That is to say, you should follow Zaitsev's rules for major and minor products. You need to make sure that you can identify a major product based on the substitution pattern that's found around the alkene. And that has to do with hyperconjugation, as we mentioned earlier. The second reaction was the complement to the reduction. That's the oxidation. And for oxidation, there were two options. We had PCC, and that one would take a primary alcohol to an aldehyde. And that was selective because if you use a stronger reagent, that stronger reagent would end up taking a primary alcohol to a carboxylic acid. It would oxidize it up to the higher state. And then the stronger options are down there. You've got the KMNO4 and the CrO3. Those would both be an acidic medium, and they will take primary alcohols up to carboxylic acids, or they will take a secondary alcohol up to a ketone. And I have a note here. Remember that we discussed you are not able to oxidize tertiary alcohols. So those are not candidates for oxidation. 3, we had halogenation. We spoke about how if you're in a tertiary alcohol situation, you can use acid halides like HCl or HBr. This is going to create water out of the alcohol, and then when the water leaves, the halide will substitute in order to give you an alkyl halide, and then that halide could be used for additional substitution reactions. If you have a secondary or primary that would not be suitable for hosting carbocations, you can use PBr3 or SOCl2 in order to create bromides and chlorides respectively with those reagents. And then to finish up, we finally discussed protection of alcohols. We only protect alcohols when it would be required, meaning the alcohol would interfere with a reaction. And then we utilized TMSCl, which was trimethylsilyl chloride. That would create a silyl ether, and we can recover that alcohol by cleaving the silyl ether with acid and reprotonating the oxygen that's found behind there. So that covers the entire summary as far as what we learned with alcohols. So thank you very much for taking the time to learn with MCAT ACE, and we will see you for future lectures.